One of the most annoying things to do when you are taking calculus class is taking the derivative of a function using the definition of the derivative. So in terms of limits, you have that the derivative of the function f of x is equal to f of x plus h minus f of x divided by h. And this is just taking the slope of the line at x a space h away as you shrink h smaller and smaller and smaller. And while this definition makes sense, it's actually quite nice to be able to think about it in this way because it's just like Pythagorean's theorem. What's unfortunate is that it's really freaking annoying to use. As such, it's so nice to be able to use the power rule, which is a lifesaver in calculus class. So instead of having to do these annoying ass polynomial limits, now you could just take the derivative of a function that is specifically a polynomial by bringing down the exponent down in front of the function and subtracting it. So for example, if I wanted to take the derivative of the function x squared, so say we're taking the derivative d dx of x squared, well, the power rule says that you just bring this exponent down to the front and subtract 1 off. So we would get that our answer would be equal to 2 in front times x to the power of 2 minus 1, which is just 1. So our answer is 2 times x. Pretty easy. Okay, let's do another example. If I had the derivative of x to the power of 5, well, same thing, just bring down the 5, subtract off 1, and we get 5 times x to the power of 4, because 4 is 5 minus 1. It turns out that this also is the same process no matter what actual exponents you have. So for example, if I was to have the derivative of x to the power of -2, if you do that, you bring this -2 down, and then you subtract 1 off. So this just becomes -2 times x to the power of -3. And it even works for fractions, or not just fractions, but actually any real number. So if I was to, for example, say, want to take the derivative of x to the power of pi, well, we just bring the pi down, subtract off 1, and what do we get? We get that this is pi times x to the power of pi minus 1. Pretty straightforward. I think that anybody who just spends 5 seconds with this can kind of grasp what the power rule is doing. But it's one thing to be able to use it, and it's another thing to be able to understand why it works. So let's actually go through a proof to see what's going on here so we can actually explain and understand why we can do this. And this proof is, in fact, going to use the limit definition. So I know that I was just railing on that and shit, but it is what it is. So let's say we want to take the derivative, for example, right now of just x squared. And we'll expand this out to a more general case in a minute, but let's take the derivative specifically of x squared because it's going to make us not want to jump off a bridge. It'll be pretty straightforward. Okay, well, the limit definition says if I take the limit as h approaches 0 of x plus h squared minus x squared divided by h, well, that should give us our derivative. This isn't so bad. Let's just simplify this out. This is equal to the limit as h approaches 0. Let's expand this here. Well, some motorcyclers are just outside my apartment. X squared plus 2x times h plus h squared minus x squared. Well, this x squared and this x squared, I'll divide all that by h. That x squared and that x squared cancel each other out. And this h cancels out with this h and this h. So we end up with this being equal to the limit as h approaches 0 of 2x plus h, and this term just goes to 0, which means our limit is just 2x. And that kind of went off the screen, but 2x. Okay, pretty straightforward. How can we expand this to not just x squared, but something potentially a little more complicated? We do need to take advantage of something that you probably haven't learned if you're just in elementary calculus, which is called the binomial theorem. And what the binomial theorem says is that if you have some expression, x plus h, for example, to the power of n, that is going to be equal to the sum starting at j equal to 0 all the way up until n. You have to sum up n, choose j, times x to the power of j times h to the power of n minus j. And that looks like a lot, but it actually turns out to just be pretty intuitive. Like once you get the hang of it, you'll do in like discrete mathematics or group theory or something. I'm not going to prove this here, but what it's saying is it's giving you the different coefficients for all the different powers. So if I had x to the power of h to the power of 4, we would have not just x to the power of 4, but we would also have x to the power of 3 times h, and then x squared, h squared, and then x h cubed, and then h to the power of 4, all of this being in the wrong spot there, but h to the power of 4. And then this just gives you the coefficients that go in front of each of these respective slots. The exact details actually won't really matter all that much for our purposes, but let's use this to actually solve out or prove our general case. So we want to know what the derivative of x to the power of n is equal to using the limit. So as h approaches 0. So, well, okay, we have x plus h to the power of n minus x to the power of n divided by h. We can now expand this using the binomial theorem. And if we expand this using the binomial theorem, we get that this is equal to the limit. And I'm sorry, my limit symbolism, oh, it's so garbage, but it's in cursive. And cursive is a thing that we were taught in schools back in my day, which was a long time ago. If we expand this out using binomial theorem, what we will eventually find, and these are the only terms that really matter to us, we will have x to the power of n plus n times x to the power of n minus 1 times h plus a bunch of other terms that are irrelevant, because what they will have is they will all have at least some power of h that is bigger than 1. So it'll be like h squared times something. So let's represent this as h squared times a bunch of other stuff that's not actually really that relevant to us. Minus x to the power of n divided by h. This x cancels out with this x. This h cancels out with this h. This h squared cancels out and just becomes h. However, what we find is that this becomes equal to the limit as h approaches 0 of n times x to the power of n minus 1 plus h times a lot of stuff that we don't really care about, because all of this goes to 0 as h approaches to 0, because this right here approaches 0. So then this is just equal to n times x to the power of n minus 1. Let's fucking go. All right, good shit. However, you might have realized that this proof relies on the binomial theorem, and an astute observer who's probably not a calculus student would be like, hey, the binomial theorem only fucking works for like integers. What do we do if we're not dealing with an integer right now? Well, it turns out that in order to be able to prove this for non-integers, you need to have the chain rule. But I will show you what one of those proofs using the chain rule actually looks like, because I think it's pretty cool. And maybe that's just me because I'm a nerd, but you know, whatever. Suppose I had some value, let r be an irrational number. So suppose we have r be something like pi or square root of 2, not necessarily a fraction, not necessarily an integer. So let r be some irrational number. Well, if we want to take the derivative of x to the power of r, that's the same thing as taking the derivative of e to the power of r times the ln of x. And that's just because what you could do is you could just take the ln of this expression. It will bring down the r, and then you're taking ln of x, and then you raise that to the power of e, which is just the inverse of that function. So it's all fine and dandy. It's all the same. So what we find is that we can perform the chain rule of this entire operation. So this entire thing is going to be, well, the derivative of e to the power of r times ln of x. And well, e to the power of anything is just itself. So this is going to be e to the power of r times ln of x times, and by the chain rule, we also must take the derivative of what's inside of here. So this is the derivative of r times ln of x. R is just a constant, so it doesn't really matter to us. And ln of x, the derivative of that is going to be 1 over x. So then this whole expression evaluates to e to the power of r times ln of x times r over x. But Remember that this is just the inverse of x to the r. So this whole thing is x to the power of r times r over x. And we can cancel out one factor of x here, which makes this equal to r times x to the power of r minus 1. Now note that since we used ln as part of this proof, we need, in this case, x to be bigger than 0. However, we are not dealing with complex numbers. We're not worrying about any of that shit. We are just dealing with real numbers here. So that is totally fine because, like, what would it even mean to have something like negative 2 to the power of pi? Like, that wouldn't make any sense for our non-complex situations. So with that, I think we are good on the power rule. Let me know if there's anything else you want to see.